Kia ora. Today we're looking at carboxylic acids. Carboxylic acids have a general formula RCOOH, where the functional group, or the reactive part of the carboxylic acid, is the COOH. Now if you look at the diagram, you can see that the carboxyl group, the functional group, the carbon, it has a double bond to an oxygen, a single bond to another oxygen, which is also bonded to a hydrogen. So we've got 4 atoms in this functional group, C double bond O, OH. Remembering that the functional group is C double bond OH, can you tell which of these are carboxylic acids and which aren't? If we have a look at this first structure, we can see we've got C double bond O, OH. Is that a carboxylic acid? Yes, it is. That's right. What about this one here? It's got a C double bond O, OH. Is that a carboxylic acid? No, you're right, it isn't, because the OH group there is not bonded to the same carbon that the double bond O is bonded to, so that is not a carboxylic acid. What about this one here? We've got the C double bond O, but no OH group, so that is not a carboxylic acid. What about this one here? That's right, even though there are 2 C double bond OH groups on this structure, it is a carboxylic acid, a dioic acid if you like. So when we name carboxylic acids, usually we've got an alkane base, so all the carbons have single bonds. That means we can take the alkane base name, or parent name, and just replace the E on the end of the name with an oic acid. Now you'll notice that because the C double bond O OH functional group only has one spare bond off the carbon, the carboxylic acid functional group has to be on the end of the chain. Because it has to be on the end of the chain, that carbon is always numbered 1, therefore we don't need a number for the oic acid. Unless, of course, there's more than one carboxylic acid functional group in it, but we'll have a look at that in a minute. So the first 4 carboxylic acids, the smallest 4, are the ones with 1 carbon in it, methanoic acid, 2 carbons, ethanoic acid, 3 carbons, propanoic acid, 4 carbons, butanoic acid. Now, that follows the same naming as all the other organic compounds, meth, eth, prop, bute. You must know those prefixes, meth, eth, prop, bute, then pent, hex, hept and oct. You'll see here I've also got a list of common names of the carboxylic acids. You don't need to worry about that too much, but as a point of interest, methanoic acid is often called formic acid, and you may have heard of that before, and acetic acid, it's ethanoic acid. And you might associate ethanoic acid and acetic acid with vinegar, because vinegar is about 6% ethanoic acid. That distinctive vinegar smell is the smell of ethanoic acid. So if we look at this structure here, what carboxylic acid is that? If you said ethanoic acid, you'd be right, because it has 2 carbons in it. This structure here is ethanoic acid. The carbon in the functional group does count. So, can you match the names with the formulae for these carboxylic acids? Pause the video if you like, to give yourself some time to match these up. Is this what you found? So why are compounds containing the COOH group called acids? Okay, in aqueous solutions of carboxylic acids, universal indicator can turn red, yellow or orange. Okay, if you think of the Roy G. Biv way of remembering the colours of universal indicator, Roy represents the acids. And because carboxylic acids are weak acids, we would expect to see orange or yellow for weak acids, but sometimes you might get red as well. What about litmus paper? What would litmus paper do in a carboxylic acid? Hopefully you remember that litmus paper turns red in acid. Okay, remember? Acid with the D on the end turns litmus red, also with the D on the end. And base, capital B, turns litmus blue, B and B, D and D. It's a good way to remember litmus and its changes in acids and bases. But all carboxylic acids are weak acids, so they set up that equilibrium in water. And we've learnt about equilibrium already this year. So have a look at this functional group, and you see that the H here on the carboxylic acid is the one that is removed and donated to the H2O, the water, not one of the hydrogens off the CH3 group. That's not the functional group. So it's only the hydrogen from the functional group that is lost. And that means we end up with H3O+. You can see here it's written in a condensed form, so it might be easier for you to read. And the other part of the acid is left with a minus charge. Because H+ has been donated, your proton has been donated, then we're left with a negative charge on the carboxylate ion. Okay, so we've got this structure here with the minus, the ethanoate ion, and H3O+, the hydronium ion forming. Now because we've got more H3O+ in solution, that's going to impact on the pH. So pH will drop below 7, and that's why carboxylic acids are acids. They're able to form the H3O+ ion in solution. So carboxylic acids dissociate to some extent in water. They are weak acids, so they don't readily dissociate. Okay, and what we need to remember there is that not all acids are the same. They have different degrees of dissociation, so that means that different amounts of hydronium ions are formed with different acids. So they're not all going to end up with the same pH. But the pH will still be below 7. So how do these carboxylic acids react? In fact, they react in exactly the same way as other acids react. So they do react with metals, and if we have a look at the example of ethanoic acid with magnesium metal, we can see that it forms the structure here. Again, the ethanoate ion and magnesium ion and hydrogen gas. Remember, an acid and a metal gives you a salt. In this case, it's magnesium ethanoate. And hydrogen gas. Just like any metal acid reaction, you get a salt and hydrogen gas. If we look at ethanoic acid with metal oxides or metal hydroxides, just remember that metal oxides and metal hydroxides are bases. So this is an acid-base reaction. Okay? When we've got an acid-base reaction, we end up with a salt and water. It's a neutralisation process, so water is produced. So we end up with, in this case, copper ethanoate and water. And a third reaction is with the carbonates. Now acids react with carbonates and hydrogen carbonates in the same way, so they get the same products. In this case, we get 3 products with this type of reaction. Okay, so we've got ethanoic acid again reacting, this time with sodium carbonate. So we end up with sodium ethanoate as our salt, plus carbon dioxide and water, because acids, when they react with carbonates, form a salt, plus water, plus carbon dioxide. Again, we've got water forming, so it also is a neutralisation reaction. How are you going? You're keeping up with what we're doing here? Now, let me just flick through those pages that we've just seen to have a look at some real-world examples of methanoic acid. Okay, methanoic acid, the smallest of the carboxylic acids, gives a nasty sting, and it's found in nature quite a lot. We see it in bees when they sting us. It's methanoic acid that creates that welt, and you can see a sting up on this person's arm here. And stinging nettle and the tips of its leaves, where its wee needles are, it also has formic acid. And of course ants, when they bite, they're injecting formic acid in as well. All of these things sting terribly, and if you think about it, if you've ever had an acid in a cut, it stings like crazy. What other examples of carboxylic acids can we think of? Well, there's the one already mentioned in this video, vinegar. Ethanoic acid is found in vinegar. Cheese, as it ripens, produces propanoic acid, and rancid butter can owe part of its smell to butanoic acid. And you may well be familiar with the smell of butanoic acid. It's not very pleasant. It's that vomit smell. That vomit smell is due to the production of butanoic acid in your stomach. So next time you have the misfortune of vomiting or losing your tummy contents, just think, it's butanoic acid causing that smell.